Good morning to everyone. I am Padovani, a PhD student at Politecnico Milano, and today I will present you the paper whose title is on Amplitude-Gain-Control Optimization for Lissajous frequency-modulated MEMS gyroscope. The amplitude-gain-control loop is often used in amplitude-modulated MEMS gyroscope to control the displacement amplitude of the mass in the right direction, compensating both part-to-part variabilities and slow changes of the quality factor. It aims at pick up a voltage at the output of the front end of the electronic oscillator to retrieve a signal which is proportional to the displacement amplitude through a mixer and a low-pass filter, and then it compares it with a voltage reference and closes the negative feedback loop through the acting on actuation circuit such as an edge bridge. But the question arising here is this circuit structure suited to a frequency-modulated gyroscope? So the following presentation will mainly focus on the challenges related to the AGC implementation within a Lissajous frequency-modulated MEMS gyroscope, and a solution is exposed here. So in this topology, the mass is driven at the resonant frequency in both axes, which are purposely mismatched, and the resulting harmonic trajectory has a period equal to the inverse of the frequency difference. And the Lissajous trajectory here shown brings back a modulation of the resonance frequency from which the angular velocity can be extracted. However, for the purpose of the paper, it is essential to remind that the Coriolis force not only modulates the frequency but also the amplitude of the displacement and in turn all the currents and the voltages of the electronic oscillator. By taking into account the amplitude-modulated contribution, the design aims at leaving the frequency-modulated contribution without distortion, while attenuating the spurious tone at the twice of the resonance frequency created by the mixer. Often in amplitude-modulated gyroscope there are two main control strategies. So first of all, the proportional AGC, which however within this topology create a distortion of the Lissajous pattern, as we can see from the figure, since the phase of the reaction of the negative feedback loop is not the proper one for a perfect amplitude modulated compensation, as we can see from the magnitude and the phase of the loop gain of the proportional AGC. Another solution could be the extended bandwidth AGC, which however does not give sufficient attenuation at the twice of the resonance frequency. So the solution exposed here is an integral type AGC, which is not reacting at all at the split frequency, avoiding any distortion of the Lissajous pattern. So the figure reported here is the fully integrated chip, which contains not only the two oscillators and the AGCs, but also the frequency to digital converters and the digital processing part needed for a Lissajous frequency modulated gyroscope to work properly. The integral type AGC controls only the DC amplitude of the oscillation without reacting against the amplitude modulated effect at the split frequency. The implementation lies on a switching capacitor topology with a clock frequency of 1 kHz. And here is reported also the magnitude and the phase of the integral type AGC, where we can see that the nominal pole of the integrator let the gain bandwidth with product be placed before the pole of the MEMS at 2.5 Hz. However, the startup time of the integral AGC is too large, in the order of seconds, so a fast feed-forward path is included. So a dual mode AGC is created, an integral type used only at steady state and a proportional type 1 used only at the startup being the integral type AGC completely idle. So here is deported the structure of the two paths, one with the gain stage and the other with the integrator stage, and is also reported the magnitude and the phase of the proportional type AGC. All the integrated circuit is implemented through a 0.13 micron STMicroelectronics CMOS process. However, in order to let the system work properly, the slow AGC needed a precharge phase, during which the feedback capacitor is precharged to the DC output voltage of the proportional type AGC. However, two main problems arise. So, first of all, the gain of the precharge phase should be maintained equal to 1. So, because of the F delta spreads, the effective value of the feedback capacitor is selected through a counter to compute the current average, which follows the F delta spreads. The second problem regarded the spurious tone, which is superimposed to the output of the proportional type AGC, and in this topology it is cancelled through a reset of the feedback capacitance once every delta frequency, avoiding the continuous integration of the output of the proportional type AGC until the AGC changes mode to the integration phase. So to manage the switch from the fast AGC to the slow AGC, an automatic switch controller is here implemented, and it sends the output voltage of the different amplifier through a double threshold, which is placed at 100 millivolts. And from the figure here, it shows the measure time transitory, which lasts for 40 milliseconds due to the large bandwidth of the proportional type AGC. Then we can also clearly see the ripple at F delta, and due to the AGC proportional type. And then once the feedback capacitor of the integrator path is correctly precharged to the DC output voltage of the proportional path, the automatic switch controller activated the slow AGC, deactivating the fast one. Overall, the startup lasts 100 milliseconds. So the measure frequency noise spectrum confirms that no additional noise is introduced with respect to an IGC-less circuit around the split frequency. So to summarize, an integrated dual-mode AGC is implemented for a Lissajous frequency-modulated gyroscope, avoiding the distortion of the Lissajous pattern while fulfilling the stability constraint of the negative feedback loop, while achieving a fast build-up within 100 milliseconds. And it maintains a resolution of 6 mDps over square root of hertz at the split frequency, and it is not affected by low frequency noise of the AGC thanks to its reduced bandwidth. So that's all. Thank you for watching, and we'll be glad to answer all your questions in the live chat, or please send me an email.